Hello, so in today's video, we're going to look at several relationships between variables, several proportional relationships between two variables. So you would have seen earlier on in your education in maths, you would have seen or heard of the concept of direct and inverse proportion. So this is basically just a summary of direct and inverse proportion. We're just going to summarize some key proportional relationships between variables. So if we just look at the first one here, so y is directly proportional to x. So yeah, if you just remember that this symbol here just means proportional to, I'll just make a note of this just to remind ourselves. So this symbol just means proportional to. So we've got a variable y, which is proportional to a variable x. Okay, so for example, the example that I put in brackets here. So c, which in this context means circumference, equals 2 pi r, so 2 times pi times the radius. So that tells us that c, the circumference, is proportional to the radius, because if we remember, y being proportional to x just means that y equals k, a constant, times by x. So in this case, our constant would be this 2 pi there. So c is proportional to the variable r. So that's our first one. And then the second example here, so y is proportional to x squared. So in other words, y equals a number times by x squared. So yeah, for example, it could be area. So area is proportional to r squared because area equals pi r squared of a circle, for example. So yeah, that could be another example. We've also got this y is proportional to x cubed one here. So yeah, for example, volume is proportional to the radius cubed because you have this constant of proportionality 4/3 pi. So that's that example. Similarly with this one here, so y is proportional to 1 over x. You can also call this inverse proportion as well. So you can also say that y is inversely proportional to x. So that's just another way of saying that y is directly proportional to 1 over x. Sorry, let me write this again down here. So y is proportional inversely proportional to x. Okay, so that's this example here. So yeah, for example, you could have resistance equals voltage over current. So this is just a physics formula. So if voltage is a fixed number, for example, that means that resistance is directly proportional to 1 over the current. So yeah, we can determine that just by that, and the constant of proportionality in this case would be our voltage there. Then example number 5. So y is proportional to 1 over x squared. So yeah, an example of this could be another physics formula, could be intensity. So intensity is equal to power divided by 4 pi r squared. So let's just say that power is a fixed number. That means intensity is proportional to 1 over r squared with our constant p over 4 pi. But we'll come on to this in a minute. So we'll go through all of these examples in detail in a second. This one here, so y is proportional to a to the power of x. So this is kind of like an exponential model. Let's just make a note of this, that this is an exponential model. Exponential models. We'll come on to this in future videos, actually, these exponential models. Yeah, if we just assume that a is a bigger number than 1, again, we'll see why that is in a minute. We could have something like this, so a population growth model. So population equals a number times a to the power of t, so rate of growth. So that tells us p, the population, is proportional to this this a to the power of t with a proportional constant of proportionality p0. Similar kind of thing here. This is actually an exponential decay model because of the negative sign there and the fact that a is bigger than 1. But again, we'll come on to this in a second. So this is growth, exponential growth, and this is exponential decay in there. Okay, and then our last example, so y is proportional to the square root of x. So for example, we could have s is equal to a half at squared. So this is something similar to what you may have seen in mechanics if you've done some mechanics. So t is proportional to the square root of s. So if you square root both sides, well, if you rearrange this, you get s divided by, 2 times s divided by a equals t squared. If you assume that a is just a fixed number, square root both sides, you get that t is equal to the square root of 2s. But again, we'll come on to this in detail now. Okay, let's go to the next page. So yeah, so let's say we've got c equals 2 pi r. So in other words, c is proportional to r. What would the graph look like? Well, the graph's just going to look like this. It's just going to be a straight line linear graph through the origin. The key thing is this goes through the origin there. There's no additive constant. There's no additive constant there, so we don't need to like shift the graph up or down on a y-intercept other than 0. This is our graph here. So this is the graph c equals 2 pi r, and our gradient, which you can probably tell, is going to be this 2 pi r. Sorry, this 2 pi. Sorry, my bad. So your gradient, your change in c divided by your change in r. Your gradient, I'll just call it grad for gradient. So your grad is going to be equal to the 2 pi r, the constant of proportionality. So yeah, that's kind of how this relationship works. Now, how about this relationship where a is directly proportional to r squared? How about this relationship? Well, if we sketch a graph of a against r, so in other words, a equals a number times r squared, it's going to be like a quadratic shape. So this kind of parabola shape. I mean, this is a real life formula, area equals pi r squared of a circle. So I mean, you wouldn't have a negative side, but technically you could have a negative side as well. So I'm just going to dot that in, because technically you could also have the negative end as well. But in real life, obviously, you're just going to have the positive r values because you can't have a negative radius. So yeah, that would be our relationship. Now, how about if we sketch a graph of a against r squared? Okay, so this is actually just going to be a straight line gradient. So a straight line going from the origin again. Again, technically you could have a negative part there, but again, you can't have a, well, actually, no, sorry, my bad. That's incorrect. You can't, when you square a number, you will never get a negative value anyway, because any number squared is always bigger than or equal to 0. So actually there's no line going down here. It's only the positive half line here. So yeah, that would be our relationship. Because yeah, a is proportional to r squared, so a against r squared on a graph would look like this, and our gradient, as you can probably guess, is going to be pi, this proportional constant, this constant of proportionality. So our change in a divided by our change in r squared, that's going to give us a gradient of pi, and we can see that from our formula there. So that's our second example. How about this one? So v equals 4 over 3 pi r cubed, so the formula for a sphere. Again, this is telling us that v is directly proportional to r cubed. So again, if we sketch a graph of v against r cubed, so cubic graphs kind of go like this, don't they? So kind of, well, the usual y equals x cubed graph goes something like this. So a v against, sorry, a v proportional to r cubed graph gonna look something like that. Again, I've just dotted in the negative sides there because technically you can't have a negative radius in real life. But if you were dealing with variables that could be negative, you would have this negative end as well. Now, if we sketch a graph of v against r cubed, again, it's going to be a straight line. Technically, you could have a negative r cubed value, because actually when you cube a negative number, you get a negative number. So if you could have a negative number there, then you would have a continuing line down there. But just because this is a real life example, I'm just going to use dotted lines again. But if this was a mathematical example, you could continue that line solidly in the negative half as well. So again, that's how that would look like. And our gradient, as you can probably guess, is our constant of proportionality, this 4 over 3 pi. Okay, so that's that one. Now, how about this one? So let's just say we've got the formula resistance equals voltage over current. Let's assume that the voltage is a fixed positive number. I mean, in real life, you get positive voltages. So let's just assume that. So yeah, if we sketch a graph of R against I, the key thing again with this one is that R is proportional to 1 over I. So it's inversely proportional to I. So it's going to be a kind of a graph like this. You're going to get a graph like that, this like reciprocal shape that we've looked at in previous videos. So this 1 over X shape. Again, technically, you can have a negative end as well if you're dealing with just purely mathematical variables. But with these physical variables, I mean, you don't get negative voltages, sorry, negative currents and resistance, as far as I'm aware. So yeah, you could in theory have this negative end as well, but in this real life example, you wouldn't need this end there. So then again, if we put a graph of resistance against 1 over voltage, so again, we're going to get this straight line kind of thing going on. I'm actually just going to put like an open circle there, because if current was equal to 0, then 1 over 0 would be undefined. So actually, I'm just going to make clear here that we can't have current equal to 0 in such case. However, yeah, we've got this positive gradient shape again. Well, assuming v is positive, of course. If v was negative, then actually what would happen, let's just put a graph of this in, a sketch of this. So if v was a negative variable or a negative constant, so if v was negative, you get something like this instead. So actually you would get the reverse of this. You would get something like that for when v is negative. Again, in theory, you could have, in mathematical theory, you could have the graph continuing on like this. But because in real life, you don't get the negative resistance and currents, we're just going to do the positive straight line like that there. So yeah, that would be that example. Now, how about this one? So this formula here, intensity equals power over 4 pi r squared. Again, you don't need to know these formulas. These are physics formulas. But I guess they could come up because they are applications of maths. So yeah, so this tells us that I is proportional to 1 over r squared. And we've got this constant of proportionality, this p over 4 pi. Again, we'll just assume that p is bigger than 0. Now, we know how to sketch y equals 1 over x squared because we did that in previous videos. So we're basically sketching I equals 1 over r squared. So it's going to be a sketch like this. Again, in theory, you can't have a negative radius. So in theory, we would have this negative end here of the graph as well. However, in real life, again, we don't have the negative radius there. And again, how would this look like if we sketch I against 1 over r squared? Okay, so in this case, we're going to have our discontinuity at 0 because if r is equal to 0, 1 over 0 is undefined. And again, we have this straight line relationship like that. Now, again, if we've got a negative, you know, a negative value for 1 over r squared, what would that look like? So in that, well, actually, if we think about it, r squared is always bigger than 0 if r is bigger than 0, and if r is less than 0 too, because when you square any number, it's never a negative number. So 1 divided by a number which is negative, 1 divided by a number which is never negative will never be negative. So actually, you're not going to get any 1 over r squared values there. So it would just be this graph here. Yeah, so that would be our graph for this. So I against 1 over r squared. And of course, again, if you had a negative p value, a negative power in theory, your graph would actually look, sorry, not like that. It would look like the reflection of that. So something like this. And your proportional linear relationship would be that. And our gradient in this case, just to go through the gradient for this one. So our gradient would be this p over 4 pi, because that's our constant of proportionality in this case here. Okay, let's go to our next one. So we've got two examples here. So we've got this population growth model. So P basically stands for population. So population equals P0. Now P0 is supposed to represent the initial population at the time of recording. But again, when we do these exponential models in future videos, we'll go through this in more detail. But yeah, you've got P is proportional to, so P is proportional to a to the power of t. Now, a is a bigger number than 1. So what that means is that you've got exponential growth, because if you substitute in any number bigger than 1 into that and raise it to a power of t, and you keep on increasing t, you will get an exponential growth model. So you're basically going to get a growth starting from this value here. Now, this initial value here is when t is 0. Substitute t equals 0 into this formula. What do you get? Well, a to the power of 0 is the number 1. Anything to the power of 0 is the number 1. 1 times p0 gives you p0. So our initial position is going to be p0. And then we've got this exponential growth, because when you substitute in bigger t values on the x-axis, well, a to the power of t getting bigger and bigger, you're going to get exponentially bigger p values here, p coordinates here. Technically, again, we could have a negative n like this, exponentially tending to 0. But obviously in real life, if you're dealing with population, you're not going to have, you're not going to be having negative times, because you can use it to go back in time and look at previous times in previous years. But if you're measuring future times using a model, you're only going to be interested in your positive times. And again, if we sketch a graph of population against a to the power of t, it's going to be something, well, it's never going to be equal to 0. That's the key thing, because when you substitute in well, I mean, a to the power of, so a number bigger than 1 to the power of any number will never equal 0. It can get close to 0 if you get a number very negative for t. So a to the power of minus 10 to the power of a million, you're going to get very close to 0, but you'll never technically get to 0. But again, it's this straight line relationship like this straight line proportional relationship. And our gradient for this, so gradient will be p0 there. Now, again, if we've got negative t values, what will actually happen? Well, if we've got negative t values in this case, sorry, apologies, not a t, negative t value, sorry, not negative a to the t values. So, I mean, again, that's actually not possible if a is a, so if a is a bigger number than 1, so for example, the number 2, so 2 to the power of any number you like, basically, you're never going to get a negative a to the t value. So actually, we don't worry about these x coordinates again on the negative side because it's impossible. Now, again, if we had a p0 value negative, what you'd get is actually something like this instead. So you get a graph like this going through p0 there, and then this exponential like negative decay there for p0 being less than 0. Similar thing here, if that was the case, you would get a graph like this for p0 being less than 0. And our gradient, again, is, as we said, p0 there, reflected by this value there. Yeah, so that's the key thing to note with this one. And then this one here, so this is an exponential decay, and that's because, and it's decaying because this time we've got the negative t there. So if you think about it, pick a number bigger than 1, could be 2 to the power of minus 1, then do 2 to the power minus 2, 2 to the power minus 3, 2 to the power minus 4. So the bigger the t value, the smaller and smaller and smaller your number there is going to get. So it's going to be a decay graph. So it's going to be something like this. Again, substitute t equals 0 into this. You get a to the power 0, which is 1. 1 times a to the power, sorry, a of 0, sorry, 1 times a0 is just a0. So this is going to be your a0 value there. And then we get this exponential decay, which is tending to 0. It will never actually touch 0 because, again, a number bigger than 1 to the power of anything, you'll never get 0. Even a number between 0 and 1, 0.5 to the power of anything, you'll never get 0 technically. So again, you could have numbers before, if you have negative times, or a variable which takes negative numbers, you could have this negative part of the graph as well. And then, yeah, so again, our graph for this, our graph is always just going to be the same kind of thing. Again, we can't exactly be equal to 0 because a to the power minus t will never exactly be 0. But we're going to get this straight line gradient there going like that. And our gradient, again, must be this a0 value. Because, again, we can say from here that a is proportional to little a to the power minus t. So we've got a constant of proportionality of a0. So that's our gradient for this. A against little a to the minus t graph. And again, if we had a negative a0 value in theory, the graph would be like this, said the reflection of that graph. And again, the key thing why I've specified that a is bigger than 1 is because, again, if you think about it, if this number there is a number bigger than 1, then this p value is going to exponentially increase, because a number times by a number to the power of a number, well, you keep on increasing this number in the power, you're just going to exponentially increase this value there. Now, if this was a number less between 0 and 1, it would be a decaying graph. So it'd actually be this one down here if a was less than 1, or between 0 and 1. If a was actually less than 0, you wouldn't get these graphs at all. I mean, you wouldn't be able to sketch it because you're doing a negative number to certain powers, and negative number. So, for example, a negative number to the power of minus 2, or a negative number to the power of half, for example, so the square root of a number, I should say. You can't do that in real variable maths. So, yeah, that's just the key point why I've put the a bigger than 0 stipulation there. And again, if you had the negative p value, a value, so negative a0 value, and this is for a negative a0 value as well, but the gradient is still going to be a0 in those cases. And then our final example then, so yeah, this one here. So s equals a half at squared. So if you see mechanics, this is basically displacement equals a half times acceleration times time squared, assuming your initial speed is 0. There's no initial velocity. So again, if we just assume a is bigger than 0, what will our graphs look like? Well, t against s, well, let's just actually rearrange this first, like what we did before. Times both sides by 2, divide by a, you get 2s over a equals t squared. You can then square root both sides to get t without the square is equal to the square root of 2s over a. And again, if we just do the working down here, so this is the same as t being equal to the square root of 2 over a times by the square root of s. So our constant of proportionality is going to be this root 2 over a, and again, assuming a is fixed and bigger than 0. Okay, so if we sketch our graph of t against t against s, so it's just going to be one of these like normal square root graphs. So something like this. It can be equal to 0 because when you square root 0, you get 0, so it can actually be equal to 0 down there. So a graph like this, I mean, yeah, it's kind of it's always increasing, but it's kind of the gradient is getting smaller and smaller as we go up and up and up in s values. Now, again, we can't have negative s values because when you square root a negative number like this s down here, you get you don't get real values, you get complex values. Sorry, let me put my line in back again. So it's just gonna be a graph like that. And again, if we sketch t against root s, it's our straight line graph through the middle, and our gradient is going to be equal to this constant of proportionality, the root 2 over a. But again, if we've got a negative a value, so if a was actually negative instead, it would just be the reflection over the x-axis. So it would be, sorry, let me just move this up here. Move that there. So it'd just be the reflection of this, so the negative version instead. So yeah, something like that instead for a negative a value. So a negative acceleration in this physical context. And again, you'd get your negative graph going the other way as well. So your negative line going down there. So yeah, that concludes today's video. So this video was just about going through different relationships and how you would sketch graphs of the relationship between two variables which have some proportionality between them, whether it's a linear proportion, a reciprocal proportion, a quadratic, and so on and so on. That's how you would sketch the relationships between these variables.